So, yep, I'm Brian. I'm also a PhD student at Brandeis, and my advisor is here as well, so no hard questions. So these are slides that I used to present at ICDE recently, and I added some extra stuff to it and took about some of the introductory material out, so hopefully it'll be suitable to you all as an audience. Hopefully we can keep it fairly casual, so if you have any questions, feel free to just shout them out. So our research focuses primarily on how we can apply machine learning techniques to various problems that cloud databases often face. So before sort of diving into the details, I wanted to give sort of a very basic example of, nope.
Oh, it's probably because I unmuted. Okay. There we go. Yeah.
So a very basic example of sort of what a cloud database looks like from a very, very high level. So the basic problem that a cloud database provider has to solve is sort of threefold. The first thing that happens is a user sends them a workload, a set of queries that they want to process. So let's say one query of type Q2 and 3 queries of type Q1. The first decision the cloud database has to decide is, how many virtual machines am I going to use in order to process these queries? We call this resource provisioning. So you have to look at the queries that are there, you have to look at the resources you have available, and you have to figure out how many virtual machines do I want to spin up or do I want to rent in order to process these queries. After you do that, you have to do query placement. You have to decide which one of those queries from that workload are you going to place onto which virtual machine. After doing that, you have to decide what order you're going to execute those particular queries in within the virtual machine, and we call that query scheduling. So these three tasks, resource provisioning, query placement, and query scheduling, can interact with each other in very, very complex ways. At the most basic level, we have a relationship between if I provision more virtual machines, I incur a higher cost because I have to pay for them, but my workload gets processed faster because I can process more queries at the same time. On the flip side, if we use fewer virtual machines, our cost goes down, but our queries go slower because we have to stack them up more. Unfortunately, it's not quite that simple because generally when you provide a cloud service, you also have an agreement with your client called an SLA, or service level agreement, that sort of says, all right, we guarantee some kind of performance guarantees out of your database. So in other words, we won't just take all of your queries, throw them on the slowest, cheapest machine that we have, and let you deal with the consequences. So for example, so remember our workload again is 3 queries of type Q1 and 1 query of type Q2. Imagine that queries of type Q1 have a latency of 1 minute, and that queries of type Q2 have a latency of 2 minutes. If we have a service level agreement that says, I want all of my queries of type Q1 done within 1 minute, and all of my queries of type Q2 done within 3 minutes, we can have a lot more complexity in our decisions about resource provisioning, query placement, and query scheduling. So for example, here's one particular scenario. We could decide to provision 3 virtual machines and to schedule our queries on them like this. So in other words, have 3 virtual machines, put 1 instance of Q1 on each of them first, and tack the instance of Q2 on at the end. This isn't bad. It meets our deadline, and it uses 3 VMs. Another thing to do would be to just provision 2 virtual machines and schedule the queries on them like this. In other words, put Q1 first, Q2 first here, and then 2 instances of Q1. The problem with this is that 2 queries miss their deadline. These 2 instances of Q1 aren't completed by their deadline at 1 minute. So in one scenario, we have 3 VMs with no SLA violations, and in the other scenario, we have 2 VMs with violations. So you might think, all right, it's just as simple as picking the first scenario, but it's not quite that simple either. The problem with that sort of reasoning is that the cost of violating the SLA, when you make that agreement with your client, you might say, look, if we violate the SLA, we'll give you $2. Now you have to decide, is it better to pay that $2, or is it better to pay the cost of provisioning a 3rd machine? So all of this is just to illustrate that your systems for resource provisioning, for query placement, and query scheduling have to take in a lot of information into account. They have to understand cost, they have to understand the resources that you have, and they have to understand how each one of the decisions from each of those components interact. So of course this is a well-researched area, but the problem with a lot of the existing research is that it's focused on a very specific chunk of the problem. So for example, the PMAX paper, reasonably famous paper, looks at how to place queries onto VMs. So it assumes that you've got a static number of servers, workloads come in, and all you have to decide is which queries do I put where. So it doesn't look at provisioning, and it doesn't look at scheduling. It just solves the placement problem. Additionally, the PMAX paper uses percentile-based deadlines. So before, in our previous example, we had hard deadlines for all of our queries. We said we want all of Q1 done within 1 minute. Another type of deadline would be to say, I want 95% of Q1s, or 95% of all queries to finish within a minute or two. So that's what we mean by a percentile deadline. Other systems, like the ICBS system, another also reasonably famous paper, just focuses on scheduling. So they assume, all right, you've got one virtual machine, you've got these queries to process on it, how can we put them in the correct order so that you get the best performance? And they use piecewise linear SLAs, so just another type of function. So the research landscape ends up being kind of scattered, and you have a whole bunch of different systems that can do each one of these components, but they make different assumptions about the SLAs and the performance guarantees you want to make. And even if you manage to find a row here that was all the same color, integrating them together might be difficult because your placement system might make assumptions about your provisioning system that aren't true, or your provisioning system might make assumptions about your scheduling system that aren't true. So the difficulty comes in trying to design a system that is able to kind of in an end-to-end fashion schedule these queries. So when we approached this problem, we came up with 3 goals in order to try to meet that. The first is that we wanted to generate holistic end-to-end solutions, meaning that we wanted to handle resource provisioning, query placement, and query scheduling in an integrated system. So no trying to mash things together, no trying to figure out if things lined up. The second thing we wanted to look at is instead of just using a percentage-based SLA, or just using a deadline, or just using an average, we wanted to allow for application-defined performance constraints. So in other words, without any sort of human interaction, the application says, here's a function that tells you what my performance requirements are. Now do all the scheduling for me in such a way that will meet that problem. And finally, we wanted to use application-defined workloads. One of the things I forgot to mention in those previous systems, like in the Bazaar system, they assume that your workload is like Hadoop jobs, or very particular types of joins across very particular fact tables or stuff like that. And we don't want to make any assumptions about what the user's data actually looks like. We just want to assume, all right, they've got some tables and they've got some queries. What are they going to do with it? So because of that, obviously there's a lot of problems, right? These workloads that the application define can be entirely arbitrary. The performance goals that they define can be, again, entirely arbitrary. And we can have extremely complex interactions between a scheduler, a provisioner, and a placement system. So because of that, we concluded that the best way to go about this is probably to try to employ a machine learning approach, to try to look at patterns from within these workloads and performance goals to try to come up and learn new information that we can represent as a scheduling strategy. So in that vein, we've come up with 2 new frameworks, one based on supervised learning, which I'll talk about first, and the second based on reinforcement learning that attempt to solve this problem. So the first system, which we called WiSeDB, has a reasonably simple model. Essentially, the user gives a workload specification. They say, I've got these 8 types of jobs, and here are their associated latencies. And they give a performance goal, some function that says, if you get them done with this latency, it'll cost this much. So those 2 pieces of information are provided by the user and fed into the model learner. The model learner then looks at that, does some computation, and comes up with a decision tree model. This decision tree model is then capable of taking in a new workload composed of the jobs that were specified and determining the number of VMs that are necessary and where to put those queries on those VMs and in what order. So easier said than done. The big idea here is that computing the optimal for a very, very large workload is infeasible. In the case where you have a basic deadline, it's the bin packing problem, which is known to be NP hard. So if you've got more than, say, 50 queries, you're not going to brute force and find an optimal. It's not going to happen. But we can brute force and find the optimal for smaller workloads, say of 20 or 15 queries. Those we can try every possible combination, measure the cost, and pick the one with the lowest. So the idea that we're going to try to apply is to generate many, many, many small workloads from the set of users' provided templates, find the optimal for those small workloads, and then use machine learning to try to find patterns within those optimal solutions. So the kind of architecture for the model learner is to take in a performance goal in the query templates, to generate a bunch of sample workloads just by uniform with replacement sampling from the query templates, and then creating data. So the first thing we'll do for each one of those small sample workloads that we create is we'll construct a graph that represents the scheduling problem. We'll generate the optimal schedule by finding the shortest path through that graph, and then we'll extract features from each of the vertices on that graph. After that, we'll throw that all into one gigantic training set, We'll learn a model on it, and that'll become a workload management model that'll look like a decision tree. So one of the most important components of this system is this graph, and kind of once you understand that, the rest of it just sort of falls into place. So the basic idea is that you can represent resource provisioning, query placement, and query scheduling as sort of a walk on a very, very large and complicated graph. So let's say that you have just 3 queries that you want to place, 1 query of type Q1 and 2 queries of type Q2. So you start out at the start vertex, here represented by A, where all of your queries are unassigned and you've got a single empty virtual machine. Now, from this vertex, you could make the decision to assign an instance of Q1, which would move Q1 out of the unassigned set and onto this VM. We'll call that vertex C. Or you could choose to assign an instance of Q2, which would move an instance of Q2 out of the unassigned set and place it onto the VM. From B, you could, of course, decide to provision a new virtual machine, which would add another empty VM to your set. Or you could choose to assign an instance of Q1, which would pull Q1 out of that unassigned set and move onto that VM. Now, from here, you could decide to assign another instance of Q2, which would take you to state F. Notice that state F has no unassigned queries, so we call F a goal vertex. This graph is obviously very, 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 very big. I've only shown a small subset of it here. We know that because it's an NP-hard problem, that the branching factor is ridiculous, and it can get really, really big, really, really fast. But hopefully, if the initial number of unassigned queries is small, we can use graph pathfinding heuristics like A-star or Dijkstra's in order to compute kind of the shortest path. So the other trick with this graph is that the edge weights are associated with the cost of the particular action. So here on edge AB, we say that assigning query 2 has a cost of 9. And that's because the amount of time that we have to pay to have that virtual machine for the latency of Q2 comes out to 9 cents or 9/10 of a cent, whatever unit you want to use. You'll notice here, the edge EF, the cost of assigning a Q2 becomes 50. That's because if we assign Q2 to this VM, it misses its deadline. It suffers a violation, and that violation costs us an additional 41 cents. So by assigning each weight in this graph to be the cost of performing the associated action, you can see that by finding the lowest cost path through the graph, we arrive at the optimal decision. So by using the A-star algorithm, we'll find the path A, B, E, G, J, which is great because it represents the lowest possible path from our start node to a goal vertex. Once we're at a goal vertex, we now have our entire workload assignment strategy. We know, all right, we need 2 VMs. We're going to run Q2 and then Q1 on the first one, and just Q2 on the second one. Great. So after we find that path, we next do feature extraction, because we're going to try to learn patterns from that graph. So we'll take each vertex that was along that optimal path, and we'll extract a number of features from it. For example, vertex B here will extract the features have Q1, meaning is there a Q1 available to assign? Have Q2, is there a Q2 available to assign? Cost Q1, which would be the cost of placing a query of type 1. Cost Q2, the cost of placing a query of type 2. And the wait time. So these are some example features. There's a couple more that we have in the paper. But the big idea here is that these features represent properties at that vertex, at that point in making the decision, that tell you something about what the optimal goal should be. So because of that, we know that features need to be agnostic to a couple things. First, they need to be agnostic to the actual query templates that you're using. So using a feature like, does this query use the giant fact table, won't be very helpful because one workload might have a giant fact table, but another workload might not. Second, we know that the features need to be unique to the performance goal. So one of the features that we tried was, what's the average latency so far? That feature was really, really good when we had an average latency SLA, but it was really not great. It didn't help at all when we had a total latency SLA or a percentage-based SLA. And finally, and most importantly, the features need to be agnostic to the size of the workload. So one of the features we tried was how many queries are still unassigned, right? Because that'll sort of tell us how far we are from the end. That's not a great feature because in our training set, all of our workload sizes are really small, like 15 or 20 queries. But then when the user comes along and gives us an actual workload of size 2,000, we don't know anything about what to do with 2,000 queries. So as long as your features are agnostic to these things, you can learn some interesting patterns from these vertices.
Was it significant that the value of assigning changed from 9 to 30?
Sorry, again?
What is it significant that the cost of assigning Q2 has changed from 9 to 30?
Yes, it is significant because I didn't type it right in the second slide.
So it's not significant.
but I should fix that. But the idea behind the cost, say if it actually did go from 9 to 30, might mean that your SLA changed, and now that placement would require substantially more resources. Or, yeah, that's a typo by that. Right, so after we construct this graph and we find those optimal schedules and we extract those features from each of the vertices along the optimal path, we throw them all into a giant training data pile, and we run the J48 WECA decision tree learning algorithm on it, and that gives us a workload management model. And that workload management model actually can look pretty simple. So this is one that was generated from the example you saw at the beginning. Basically, the way that you read this is you look at the current state of your setup, you extract the blue nodes, and then you follow the right lines. So probably best explained through an example. Right now, we've got one virtual machine, and all of our queries are unassigned. So the first thing we say is, all right, what's the wait time of the current virtual machine? It's 0, so we know it's less than 2, so we proceed to the right. Next, we ask, do we have a Q1 that is unassigned? Indeed, we do. Then we ask, is the cost of placing that Q1 less than 100 or greater than 100? We'll assume there's no violation, so it's less than 100. So when you reach a white box, you perform that action. So you place an instance of Q1 onto that machine. Then you reparse the tree. You ask yourself, all right, what's the wait time? The latency of Q1 is 1 minute, so our latency is still less than 2. Do we have an instance of Q1 to place? We do. Would the cost of placing that be less than 100 or greater than 100? We'll assume it's greater because now it would violate the SLA. So then we ask, all right, do we have a Q2? Indeed we do, so we place it. We made a decision, reparse the tree again. Now our wait time is 3 minutes, so we need to provision a new VM. Reparse the tree again. Wait time's less than 2 minutes. We have an instance of Q1. Its cost is less than 100. Place it. Reparse again. Less than 2 minutes. We have a Q1. Its cost would be greater than 100. We don't have a Q2. Make a new VM. And repeat.
So if we have a different workload, we have to do a new decision tree.
Yep. So if your performance deadline changes, or if the queries in your workload change, you have to retrain.
So how long to build the decision tree model?
So I didn't stick the graph in here, but we have a couple of optimizations, and for like a relatively large number of workload queries. So like in the worst case, it can take a minute or two, and in the best case, when all of our optimizations apply, we can get it under 2 seconds. So not long, but potentially, you know, if it's the worst case scenario and you're trying to build data for a live dashboard, you know,
yeah,
you have to be conscious of it.
It's not good, but for like if they have they run the analytics query for 3 seconds each and they have 100 queries, then it should be okay.
Right, yeah. So, you know, if the queries you want to schedule take half a second, then maybe not.
I just hear that you generate multiple decision trees, is that right?
So if your performance goal changes, like say your application says, oh, I told you I wanted this in 3 minutes, but I actually don't need it for 4 minutes. If there's a change to the performance goal, then you have to retrain the decision tree.
And if there's a change in how many Q1s and Q2s?
So that it's agnostic to. So the idea is that we train on these small workloads, you know, 20 queries, but then when we get the workload of size 3,000, we can use that same decision tree and try to apply the patterns we found in those small workloads. So you have to retrain if there's a new template, like a totally unseen, never before seen query. You have to retrain if your performance goal changes, but you don't have to retrain for workloads that meet those criteria. So how well does it work? Yeah.
So it looks like you're assuming the input is always going to be in the form of a document. You have a stream set of queries that keep coming in. Have you thought about
Yep. So this will show up in a VLDB paper soon, and I'll be there to present it hopefully. But so for this system, doing online query processing is a little wonky. It's possible. Basically, when a new query comes in, you treat it as a new performance goal with a slightly tighter constraint, and you retrain a tree really fast, then you do it. But the second system that I'm going to talk about today is all about processing online queries. But yeah, so there's a couple big assumptions here that I probably shouldn't have just glossed over. One is that we assume workloads come in as a batch. Second is that we assume that all of your queries are represented by a relatively small number of templates, say less than 50. And third, and perhaps biggest, is we assume that you have some kind of cost function that can take that query and tell you how long it's going to run.
So that would be my second question, right? I mean, in terms of in the vertical world, we know concurrency plays a big effect on has a big effect on latency. So do you account for how do you account for any of that? How many queries you still make over?
Right. So the multi-processing level of the VM can be configurable in our system. So you can set it higher or lower, and then it just pulls that many off the queue. But in terms of actually knowing what's going to be efficient, we sort of assume that your cost model is going to be able to tell you, which is bad, essentially. There's really no two ways about it. That's not a good assumption for highly concurrent systems. But for systems where you have that property of predictable latencies, like Hadoop jobs or a very specific set of analytic queries that you run very often to regenerate dashboards, then that assumption might hold.
So how did you classify the queries? What kind of query 1, query 2? Because the queries are different, right? But you classify them into this is a kind of query 1, query 2, query 3.
So the user flags them. So basically the user says, all right, here's my 10 query templates. And then when they submit, they say this query is template 3, this query is template 5, this query is template 7. And in the case where the user doesn't provide a labeling, we use the cost model and we say, all right, it has this latency. And then we find the query template with the closest matching latency. We'll assign that.
So I guess a cost model might be not it's a kind of classification. But I think in real life, it's kind of another project to classify query into the right set.
Absolutely. So the assumption of having a cost model that can accurately predict the performance of parallel queries is really, really problematic in a lot of database applications, probably like Vertica, but holds pretty well for other database applications, like fully replicated Postgres across a static data set. So sometimes it works, sometimes it doesn't. The second system that we'll talk about in a bit is all about getting rid of the cost model.
And do you consider any affinity between queries?
Yeah, so query affinity is accounted for in the brute forcing stage of the workloads. So basically, if let's say you've got 2 query templates and they both share a lot of data, so you want to schedule them side by side so that it's cached. When you brute force those optimal schedules for those very, very small numbers, your cost model will say, oh, hey, these are good together. And when all of your training data has those 2 queries together, the decision tree will learn a model that puts them together.
So the templates have access patterns.
Yeah. So when we first envisioned templates, we were thinking like TPCH style templates, meaning like select from this table, this table, this table, where some attribute equals question mark, and then you change the template by changing the value of the question mark, meaning that the same tables are being scanned, possibly very different parts of them, but similar access patterns. Yeah.
I say something about the interaction between the prediction model, the cost model, or otherwise prediction model, and the strictness of the SLA. So what we discovered in the experiments that we saw is that we can tolerate certain errors in the cost model. So if the prediction is like 20%, then we can handle that. But in which cases? The cases where the SLA that we have, the performance expectation, is more relaxed. Because then we build a model that has more slack in it. So we can handle putting them in their own machine, and them running longer than expected is okay because the SLA, the performance expectation, is not so strict. So there is an interaction there between how relaxed is your expectation versus how good is your prediction. But yeah, performance prediction databases, it's a very hard, unsolved problem.
Calling it bad was probably over harsh. Like we can tolerate errors up to 20%, and if your SLA is really loose, we can tolerate even higher errors. So we found that with like TPCH queries, which are like some of the most studied queries that you're trying to get a predictive model against, the best sort of prediction models that handled them in a parallel sense, we're getting accuracies between 15 and 20%. And so we figured, all right, if we can tolerate even more than 20%, then we're good. There's at least some evidence to suggest that if you really sit down with your workload, you can develop a model that can measure with that level of accuracy. So evaluating the performance of these particular models can get a little tricky. So we primarily evaluated the performance based on 2 different standards. One is we used our models to schedule very small workloads. and we compared the results of our model with the actual optimal brute force. And that's what you're seeing here. So we used 4 types of SLAs to try to demonstrate the flexibility of our system. The first being a per query SLA. This basically says that if for each one of your query templates you have an associated deadline. So Q1, 1 minute, Q2, 8 minutes, Q3, 5 minutes. Average basically says the average latency of all the queries in my workload need to be less than a certain number of minutes. Max says that the slowest query in my workload has to be less than a certain number of minutes. And percent says 90% of the queries in my workload need to be less than a certain number of minutes.
So when you say less than a certain number of minutes, like when the time, like latency when the query starts getting run.
When it finishes.
Finish.
Yeah. So
what that means, like you have to predict the runtime of query already. So you know, like this query will run 81 minutes.
Right.
And then plus the delay 3 minutes, and it will be done in 4 minutes.
Right. And 1 minute to spin up the VM too at the beginning. Yeah. So this graph this graph demonstrates that for the optimal case with the TBCH benchmark for these 4 queries, we come pretty darn close to the optimal cost. If you do the numbers, it's between 3 and 8%. So we were pretty happy with that in terms of comparison to the optimal. But the problem with this comparison is that if your workload is so small that you can compute the optimal, why not just compute the optimal? So the next thing that we did is we compared it against 3 very popular heuristics for the bin packing and query scheduling problem. And we did it for each one of the SLAs again. So for the 3 we compared against was FFD, which is first fit decreasing. Basically, it means you sort all of your queries in decreasing order. You take the first one and you put it on a VM that'll fit. Then you take the next one and you put it on a VM where it won't violate anything. You keep doing that until nothing will fit anymore. And when nothing fits anymore, you make a new VM. And you just repeat that process until all of your queries are scheduled. This is a very popular heuristic to solve the bin packing problem. It has some very nice provable upper bounds on its optimality and stuff like that. FFI is just sort of the flip side of FFD. FFI is when you're trying to you sort out your queries in increasing order, and then you place them until they don't fit, and then you make a new VM. So FFI, if you remember from your operating systems textbooks, is what you do when you want to minimize the average wait time of a job. You put the shortest job first, which pulls your average down. Pack9 is a heuristic that we made up that simply puts your 9 shortest queries in a row followed by your longest query, and then repeats that pattern over and over again. So the reason that we created the Pack9 heuristic was to sort of try to overfit and do something tricky with an SLA that says 90% of your queries need to be done within a certain number of minutes. So the idea was we'll put 9 really short queries in a row and then 1 really long query. That 1 really long query will take forever. It'll get counted as the 10% that you're allowed to miss with the SLA. So you can see for the percentage-based SLA, FFD and FFI incur a pretty significant cost. Pack9 incurs a much lower cost, and our system beats it out by a little bit.
So how many queries in your workflow?
5,000. Here.
This is a trivial thing, but presuming you're going to present these slides with 10 BLDB, it would probably be a good idea if the colors were consistent between this last slide and this slide, because the first impression.
Ooh, yeah, I switched it, huh? That's good to know. Right, so the next SLA, max. So the max SLA, which says the latest query has to finish before X minutes, is the closest to bin packing. So here we would expect FFD to do the best, and indeed it does. FFD beats out Pack9 and FFI, and we beat out FFD by a little. For average, so we would expect FFI to do the best, because putting your shortest job first will drag down your average. And again, FFD does the worst here, and FFI and WiSeDB are just about tied. And finally, for the pure query SLA, where we would again expect FFI to do the best, we see FFI and WiSeDB beating it slightly. So the point here isn't to say, oh, hey, look, we have this great algorithm that's going to get the lowest possible cost ever, and you're going to save so much money. The point here is that for an arbitrary application-defined performance characteristic, B-score, with no knowledge of it whatsoever, we can learn a heuristic that is just as good and probably a little better than if a human being were to look at that performance goal and come up with a heuristic on their own. So again, the idea isn't, oh, hey, we're totally beating the state of the art for this particular problem. It's we've built a system that can generalize over all of these different workload management problems with very good efficiency. And I think that's demonstrated here. In the paper, which you can read for free from WiSeDB, we also show its performance against online algorithms, and we show how the overhead of the training time. What else do we show? We show some other stuff too. Cost model sensitivity.
And optimizations, which
Right. Yeah. Right. So.
Do you have any numbers with traditional models compared with Bazaar?
So one of the main reasons we didn't compare directly against those other systems is because it's very, very hard to integrate, say, Bazaar, which handles scheduling and provisioning, with a placement system. And we figured that reviewers would look at whatever we did with Bazaar and said, oh, you must not have given it a very good placement system. So we didn't want to try to argue that we had done the engineering for each one of these very specific systems to make it apply generally, because that's exactly, it's really, really hard. That's our argument, right? Like, you can't take a system that's designed to optimize one particular database and expect it to work on others. Lots of other features that are discussed in the paper. One of the coolest things about the generation of these models is that it lets you explore performance and cost trade-offs. So oftentimes you think, well, how much would it cost for me to get my queries back 10% faster? And so you can use WiSeDB, and you can generate a model for one SLA, and you can generate a model for the other SLA, and you can simulate it. You can use the decision tree, you can trace it out, you can think, oh, how many more VMs would I need to make things go 10% faster? And that's pretty cool in and of itself, just as a tool to be able to have. And we talk about the specifics of how to do that in the paper. We also discuss a lot of training optimizations. So we're using the A-star algorithm to go through that graph to find the optimal goal vertex and the path to it. And some of you may be familiar, the A-star algorithm uses a heuristic, which basically says, if I'm here, what's a lower bound on the distance to the goal node? And so we talk about some of those heuristics that can make this search a lot faster and various assumptions you can make about performance goals to accelerate them. We also talk about how to handle online scheduling. The basic idea is if you have a query that comes in and then another query that comes in 30 seconds later, that's just like if that query that came in 30 seconds later came in with a 30-second stricter deadline, and you'd scheduled it at the same time. And we show how that can be efficient and how that can outperform other online scheduling systems. And we give a much fuller experimental study than the slides that I presented here. So there's a lot of advantages to this system. One is that it produces human-readable strategies. That decision tree that I showed you wasn't just a toy example. It was one that was actually generated from WiSeDB. So it gives you a strategy. A human being can look at it and be like, yep, that'll work. Or, whoa, that's ridiculous. Forget about it. Or, and a human can learn from it. Like, oh, that's a smart idea. That also gives it verifiability. It means you're not just hoping that, because, a lot of these machine learning techniques, 97%, right? That's always the number people say. Oh, it's 97%, that's good enough, we don't need to do any more work. This is verifiable. You can look at that model and there's no statistics, there's no guessing. You can say, yep, this will do the right thing. So no noise. And finally, it's train once, use forever. Once you pay that training overhead of 10 seconds to 2 minutes, you have that model, it's good forever, you can apply it very quickly to any number of queries. But it does have some disadvantages. One of the biggest ones possibly is that it depends on that cost model. It depends on the ability to take a query and say, how long is this going to run on this VM? That's a really hard problem that is still being actively researched. Second is that you can't change the query templates that you're using without retraining. So a lot of data exploration tasks, like if you have a customer who's going through trying to find or isolate a specific pattern, all of their queries will appear novel, right? It won't look like any of them are from the same template. So that's a problem because each time you generate a new template, a new novel template, you have to do retraining. And finally, when the underlying resources themselves change, when Amazon says, now we're offering this brand new virtual machine, or when all of Amazon starts slowing down a lot because there's a data center failure, or when it's 7 p.m. on a Friday and everyone's using Netflix and Amazon gets slower, those resource changes require either a very, very smart, unbelievably smart cost model or retraining to understand how those resource changes affect your queries. So to try to address some of those particular concerns, we started looking into reinforcement learning approaches to this to a similar problem. So the last approach used supervised learning, which is when you take a training set that's labeled and you try to come up with a function that takes a new unseen thing and labels it. Reinforcement learning is a little different. The idea in reinforcement learning is that you have some environment that you're interacting with and an agent that's doing the interaction. And the agent takes an action inside of the environment, like, say, kicking the soccer ball. And then the environment will say, OK, here's the new state that you're in. The soccer ball is now 2 feet ahead of you. And here's the reward you got for doing that. You scored a goal, you didn't score a goal, the other team got the ball, etc. And you hope that you find an intelligent learning algorithm that can go through this cycle and learn, with each iteration, gain a little bit more knowledge and maximize its reward over time. So one of the earliest examples of reinforcement learning is something called a contextual multi-armed bandit, or CMAB, and it emerged from the world of online advertising. The basic idea is you've got some user, you, and you visit Wikipedia. And Wikipedia has to decide, all right, we need to get people to give us some money so we can pay our server costs. So we need to choose, are we going to show them ad 1 or are we going to show them ad 2? And so you know something about the user. You know they just looked at the article for HPE Vertica, and you know they just looked at the article for Teradata. And you also know something about past users. You have some experience. You're like, people who look at a lot of database articles seem to prefer choice 2. And so based on that knowledge, you might say, OK, based on the context that you're in, you might say, I'm going to pick choice 2. To formalize that a little bit more, imagine you're at a casino, and there's 8 slot machines in front of you. And all of the slot machines are slightly different, and they all cost the same amount to play. And your goal, it's a very nice casino owner, so you know that you can win. It's possible for you to make money out of this. So your task is to figure out which order do I play these slot machines in order to get the most bang for your buck, right? So you've got $4, and you're like, all right, which ones am I going to play? So you have to balance 2 things. First is you have to balance exploitation. Say you play the first slot machine, you put in 25 cents, you get 26 back. You could just keep playing that same slot machine forever, right? But there could be another slot machine with a way bigger payoff. So you have to decide, do I want to explore? Do I want to try different options and try to gain more information? Or do I want to exploit the information that I have now? And so the balancing act between these 2 components of exploitation and exploration is exactly what the contextual multi-armed bandit represents. The multi-armed bandit being the 8 slot machines, because the slot machines are 1-armed bandit. So one of the algorithms for solving it is called Thompson sampling, and it's a very clean mathematical, nice proof, shows that it balances exploitation and exploration nicely and minimizes regret. I'm not going to go into the proof because it's boring, but I am going to talk about how we apply that to this particular problem. So now, instead of imagining that a batch of queries come in first and you've already done all this pre-training, imagine you know absolutely nothing except that there are 2 types of VMs, some very, very fast VMs and some slightly slower but cheaper VMs, and you're going to get 1 query at a time. So a user is going to hand you a query, and you have to figure out, am I going to provision a new VM, or am I going to assign this to a VM I already have? So essentially what we'll do is we'll create a tiered network of contextual multi-armed bandits. Each one of these VMs is going to play a slot machine, and that slot machine is represented up here by these 3 levers. So when a query comes in, it goes to the top left VM, and this VM plays a game. It has to say, am I going to pull the accept lever, the pass lever, or the down lever? If it chooses to pull the accept lever, that query will be processed on that VM. If it chooses the pass lever, that query will be passed to the next VM in the same tier. If it chooses the down lever, it'll be passed downward to the next tier. If you choose to pass when there's no VM to the right of you, that represents provisioning a new VM. So for example, imagine this VM looks at its context and says, wow, I have way too many queries already. I know from experience that if I accept another one, it's going to be really bad. So it chooses to pass. So then the query gets passed to the next VM. This VM looks at its context and it says, yeah, there's no way. And in fact, even if I was empty, there's no possible way that I'm the most efficient VM to handle this. So I'm going to pass it down to the cheaper tier. That VM says, you know what? This is the right tier, but I'm also way too full. So I'll choose to pass. That'll cause a new VM to be provisioned. That VM will look at the query and say, yep, I'm empty. I can definitely take this, and it will accept it, resulting in that query being processed on that VM. So the reward for choosing these various arms on the slide is the profit that you get for processing the query. If the user gave you 500 cents to process this query, and you did it in a way that spent 300 cents, then your reward is 200 cents. And everyone along the path associates that reward of 200 cents with the lever that they pulled. And by doing this, Sorry?
If you pass, if you do instantiate a new VM, that new VM has better pick accept, right?
Yes, and in fact, because if you have no data, you might choose to explore, and you might pick pass. So we say that if you're a new VM, you have to accept. We enforce that. The other thing we enforce is if you're at the bottom tier, you can't pass down into nothing. And we also enforce that if, what else? Oh yeah, that's it actually. That's all we enforce. Yeah.
So what are the heuristics behind that VM passing down? How does the machine, the middle machine, determine that it has no resources ever for which this tier could process the query? Because it's a higher tier, so it has more resources.
Oh, sorry, I didn't mean that it doesn't have enough. I mean that it's not the most efficient. Like this might be a VM that has 32 gigs of RAM, and the query might require 2 megs, and it might think, look, I could process this 4-minute query here, but that's going to cost a lot. It'd be much smarter to throw it to a cheaper VM with less RAM. That's going to do it in 4.5 minutes.
So could it be though? So this based on prior information.
Well, so for query 1, this is an arbitrary path, right? Okay. Nobody has any information. But when this is query 10,000, you may have seen a lot of examples. You may have a lot of experience to build on in order to generate those decisions. So the specifics of how it gets made are wrapped up in Thompson sampling, and if we want, I can show how it works. But like I said, it's not the exciting part.
Okay. So it also seems like pass also might have a lot of extra cost if you the end. So does that figure it all into the algorithm?
If you're if you
spinning up an VM is expensive too.
Right. So if you choose, so for example, this particular pass, the reward that goes into these polls is the profit from the query minus the provisioning cost of the VM minusing the rent period. So basically, the actual monetary value that was achieved.
Okay. So, but do the VMs themselves making the decision know whether or not it's a pass is going to cause an instantiation?
No, they don't. So we're currently still, this is still very much under development alpha, but we're experimenting with the features that are the correct ones to do it. And right now we're trying to just keep that as small as possible so that we don't throw in too much stuff and have to sort it out later. So right now we're not using that feature. It does pass create new, but we're finding it still learns. I'll show it rapidly.
Yeah. Right. So just to finish up. So so you said if there is a query that requires 2 megs for this machine of 32 gigs of RAM, so the proportion is big, but there could be a machine down the line if it were to pass that would have, that would have a utilization of 99% of its RAM, and then the optimal placement for that query could be that machine, right?
Right. So there's no guarantee for any specific query that you'll put it in the optimal place. That's NP hard. It's not going to happen, right? But what Thompson sampling does guarantee is something called minimized regret. The regret of a decision is the difference between the decision you made and the best possible decision you could have made. So that's your regret. So what Thompson sampling does is there's a great proof that shows that as long as you keep going forever, your regret bound, the maximum regret you'll have, decreases. And so as you process more and more queries, your possible regret goes down and down more and more. Of course, to get it to optimal, you'd have to run forever, which nobody wants to do. So
I don't know. I think the system that ran forever would be pretty cool.
It would be pretty cool. Physicists would be stumped. So how's it work? This is great. I realized after I switched this graph with the other one that now I have to explain 3 extra lines. But this top line right here is the global optimal. So basically what we did in this experiment is we took a set of 30 queries, we brute forced it, we found the best possible way to schedule those 30 queries, and then we repeated that set of 30 queries over and over and over again, tons and tons and tons of time. So this top line right here is, if we know all 40 queries ahead of time, what's the best we could possibly do optimizing them? This middle line here shows, let's say that I make the best decision possible when each query comes in. So a query comes in, I put it in the cheapest place it can possibly go, but I don't know anything about what's coming next. So both of these assume a clairvoyant cost model, right? They assume that you have some way to figure out exactly how long the query is going to take, exactly where it's going to go, and exactly how much it's going to cost you. This bottom line here is doing the same thing, the placement of the query to the most profitable point, but using a cost model based on the performance of each query in isolation. And so what you can see here, this curve, is we start out doing really, really bad. We're making very dumb decisions. Almost the first thing it does is put 30 queries in a queue. It takes forever and it doesn't work. But then we learn pretty fast. And by about 300 queries, we're already beating the place each thing greedily, optimally using a cost model. By about 1,000 queries, we're actually doing better than that greedy approach with the perfect clairvoyant cost model. And as time goes on, we sort of end up somewhere in the middle here, between the global optimal, the global clairvoyant optimal, and the greedy clairvoyant. So this is really cool, because without using a cost model, remember, nobody knows how long these queries are going to take. We're learning over time, implicitly, that cost model. Because a lot of times in databases, we say, oh, if I had a cost model, then I could say, okay, how long will this query take? Oh, it's more than 5 minutes, reject it. Or, oh, it's less than 5 minutes, put it in the high priority queue. Really, we don't care about the cost, right? We care about that end decision of what queue should I put it in, or should I accept, or should I reject it? So consider that first approach to be explicit model, where you model the cost of the query, and then you make a decision based on that cost. And consider this approach implicit modeling, where instead of trying to figure out what the exact cost of it is, instead we kind of skip the middleman, and we just try to learn the actual result, the answer to the question that we want to know. And this graph, I think, demonstrates that this implicit method has a lot of promise over explicit ones. So a lot of problems. Nobody runs to run 500 queries or probably even 200 queries before their system starts behaving well. So we're trying to look at ways to decrease the number of queries that are needed to converge. One of the ways that we're doing that is we're limiting the strategy space that the algorithm is allowed to explore. So like I said before, the first thing that it does almost every time, which gets $, is put all the queries on one VM. Because initially, when you pass and provision a new VM, that seems really expensive. So the first thing you try to do is you stack everything up on your own queue, and then you quickly realize that that's not a good strategy either. So one of the things we're trying to do to sort of smooth this curve out is restrict the size of the queue. We can say, look, no query is going to be less than 2 seconds. So if our deadline is 60 seconds, the queue should never be more than 30. So other things like that to try. That's just one button press. Oh. And the last thing that we're trying to look at is finding the right features, figuring out what should belong in that context, what's sort of the minimum amount of stuff that you have to have in that context in order to build this implicit model. So this is still being worked on very actively. Hopefully it'll work out. So all of these systems are obviously very researchy. They make a lot of assumptions about the types of queries that are coming in, the types of things that are being applied, and things like that that are really nice abstractions to think about to try to understand the broad strokes of a problem. But obviously, they might not be like the most applicable thing to use tomorrow. So I think that our argument can be boiled down to there's a lot of space for research and a lot of space for making database systems better by applying machine learning to things like databases and clouds and classically hard problems. That's all I got. Thanks. Those are supposed to be icons, but you can figure it out.
I have 2 different questions. So the first thing is, I feel like we have some people like when it's not a VM, but a resolve pool, right? So customers keep asking how can we send which kind of queries to the resolve pool, kind of prioritize the queries. So I don't know if you want to explore that and see if the kind of application for you to do more research or to apply your research in there. I know that we talked earlier about different possible research for organic view, but maybe another area for you to consider here. The second question I have is because of your graph, like the last graph, where you say over time you can predict something very accurately without cross model or anything. So it come up to you went to say speculative yesterday, right? We want to I think we want different things. The first thing is we want to identify the queries that run very badly and then we don't run it at all. The second thing is more relevant to this one is how can you predict the runtime of query. So my question for you here is, so if you say that if we keep running a query again and again, but in this case, we don't, most of the time, we don't have the exact query because of the selection predicate is really different, right? And the second thing is the data set will be different too. So my question here is very accurate to us. Is that possible? Like, it's a kind of question for you, like kind of possible research or possible with your experiences with a little bit query look a little bit is a little different and data set a little different. Can we predict the runtime of query too? Like, if we run those queries, like if it's like 5 seconds, it's acceptable to run the queries, and can we predict in the future the similar queries with similar data sets like 5, 6 seconds? It's another very good, research application.
So I think one of the big takeaways from this could be that even if it's not possible to predict the exact latency of a particular query, it might be possible to predict correctly the right pool to put it in. So even if we can't say, oh, it's going to take 10 minutes, we might be able to say, okay, our system overall will perform better if we put this in the medium. In terms of predicting the actual latency, I mean, I haven't been working on this problem for as long as a lot of the people who are researching it have, but my advisor probably knows better, but I don't think it's going to happen, especially with changing data. Like, I don't know.
Teradata still has a knob, right? In your resource pools, where they're playing like, query's going to run longer than 5 minutes, but run this pool. And so I don't know. I haven't actually operationally tried it, but that's certainly in their architecture.
Yeah.
So one question I have has to do with temporal shifts in workloads. Right? So one of the common patterns that you see is people run certain queries during the day, and then running queries at night. Right? And then on Mondays always stink because everyone comes in and runs a gazillion queries in your system. Right? And your CEO runs a query at the end of the quarter, and that query better run the key split. Right? So there's certain workload shape things that change over time. How does a system like this address that sort of thing?
So temporal shifts was in the workload patterns was one of the big motivations behind switching to a reinforcement learning approach. We were hoping that the algorithm would kind of be able to intelligently at least predict its first derivative to kind of say, okay, I need to scale up more, or I need to scale down now. This particular graph is a Poisson process of queries, meaning that there's very, very roughly, because I'm not going to draw right with this laser pointer, there's not a whole lot of queries, and there's kind of a peak, and then it goes down a little bit, sort of like a normal distribution, which a lot of academic papers have argued represents sort of a 24-hour period. Like there's, I don't know if anyone uses Steam. They have this great graph that shows the number of active users per day, and it's like clockwork. It's just, it bounces. So that's sort of the query. That's the model, the temporal model we're using. Right. But adapting to those temporal models is what I think a big motivation behind being able to use an implicit representation.
So this thing doesn't, for example, try to have any sort of notion of what time of day it is built into the model.
So that could potentially be a good feature. It's not one that we're using now, but it's very possible that what's the hour, 1 to 24, might actually have a lot of predictive power over what decision you should make, and that's definitely a feature we'll investigate. The trick is we don't quite want to overfit it. So one of the things I was, if this is a Poisson model and we know exactly when the peak is going to be, and then we put in this feature that's the hour, we sort of cheated, right? Because we've already decided that that's going to be highly correlated with the workload. Yeah. So we'll have to maybe get some real-world data from like the Great Computing Archive and make sure it's realistic.
So a lot of that comes to how expensive the price of missing your particular types of queries are, right? So load rates matter a lot. Kind of don't matter until you miss your load rate, right? And so there's the price on those might actually have some impact. Right. So there's a variable price to get it down.
And that is also something we sort of gloss over even here, is that we assume that after the query is done, after it's ran, you know definitively what the utility of that was. So like you can give a number value to like, this was really bad, or this was really good. It doesn't have to be perfect. It doesn't have to be like 60 decimal places. Right. But it's got to be like the right order of magnitude.
And you need to know by that query, not by the subsequent one?
Yeah, well, it can be delayed. So you can go back later and say, oh, actually, this thing I said was good, that was actually bad. But it does assume that you can eventually quantify the utility of a query's latency. Eventually.
Query 2 followed by query 1 was bad, but query 3 followed by query 2.
Right, right. So that's one of the things that's actually really good at learning. So I haven't dived into looking at the models it's actually figuring out yet. But one of the main reasons it starts beating this yellow line is because it starts co-locating queries intelligently. Basically, it'll say, okay, the first 3 VMs, these are for fact table 1. The second 3 VMs, these are for fact table 2, or for small join table or whatever. And so those stay in memory. And it learns that automatically without us telling it anything about what's in the cache or that, which is really cool. It kind of takes a while to do it, but it gets there.
So sorry, I have other thing I have to leave, but people feel free to say here for ask more questions. But I just want to let you know that Olga will say you come here again next week because then is we talk about another paper benchmarking in the my it's on the same time and place next week. And, thank you so much. But please feel free to say I sorry I have a guest, not a guest physics. But thank you so much.
I very much appreciate this. And generally, over the course of these queries running, how many VMs are you provisioning beyond what you started?
So we start at 0, and it peaks at around 8 in this example. We haven't done a lot of this yet, but when we did, so this is our biggest run, so we showcased it. We've shown very promising results at like the 20, like the 8 to 20 level, but we haven't tried scaling it really yet, mostly because it costs a lot of money. Yeah.
How many distinct queries do you have in this?
So these queries are generated by the TCH generator. So there's 22 query templates, and they vary the parameters a lot. So I think almost every query is unique.
And do any get removed for any VMs?
Yes. So this is actually a big issue we're looking at right now. Right now, the strategy is pretty naive. It's when the queue is empty, turn it off, which is really, really good when you have a high query arrival rate, but really, really bad when your query latency is 1 minute and your query arrival rate is 1 minute and 1 second. Because then the query gets processed, it turns off the machine, and a second later, it's got to spin it back up. So we're still looking at sort of smart machine learning-y ways to manage that problem. But the most basic experiment we've done is, stay on, after you run out of queries, stay on for a constant k seconds. And that seems to work okay, but results pending, I guess.
So this is the reward. Can you remind me how is the reward related to, right?
So here the reward, it's nice because we can measure it in dollars. So we're assuming a model where you're paid per query. So a client says, all right, here's 300 cents, run this query. And based on when it finishes, there's a penalty, and then we use the Amazon prices to figure out how much it costs. So here, the average reward per query is just the average profit of the database as a service provider. And the regret would be the difference between, so the regret actually here is very visible. It's the integral between this line and this line. It's the difference between what you made and what you could have done.
I'm surprised at the shape, because I would expect that you would always regret provisioning it in the end. You would always say, oh, rats, I did it, and now I have it, and I'm still paying for it because it doesn't go away instantly.
Right, so it's averaged, so that's why. So if you were to plot each point here with absolutely no smoothing.
Don't your queries go to zero profit eventually? If you miss the SLA on the query badly, you don't make any money off it.
In fact, you can lose money, and that's why it's negative down here at the beginning.
So that's why that's to offset the more the end cost, right?
Oh, I see. Oh, right, yeah. And
you
there's
just ran
also
one query at a time and dropped all the other ones on the floor. You
Right.
have to pay for the queries to go on the floor.
right, yeah. The two things that it's kind of surprising. The two things that make this problem hard are that VMs don't start up instantly, because if they did, then you would just make one VM for each query, and the SLA deadline, because if it wasn't for those, you just put them all on one machine.
So SLA is only time-based, right? Or, what kind of other fact-based rules that you have in an SLA?
So we haven't looked at anything beyond latency metrics yet. So we've looked at like percentage SLAs, average SLAs, total SLAs, and we've also very, very briefly looked at an SLA like don't use more than this many machines, but also keep my time under this. So mostly time-specific metrics. People had other ideas of things that they think were realistic and out there in the world. Love to hear them.
Like, could we do something based on maximum cost? Like something like, I want this workload done at no more than X dollar.
That's interesting. So there's sort of two. So with WiSeDB, we were pretending that we were the consumer. We were trying to minimize the cost that we needed to spend in order to process a workload. With Bandit here, we're looking at profit. Now we're the database as a service provider, right? Now we're trying to maximize the amount of money that we get from the user. So that where you stand kind of depends on what best means, right? But that's interesting, yeah. So like, what's the maximum number of queries that I can process for $20? That might be an interesting. That might be more a WiSeDB question.
So I know that sounds silly, but as the database provider, do you necessarily mean Amazon, or do you mean some service that uses Amazon?
Yeah. So our DBAAS is a middle layer.
Tier, right?
Someone who's got to pay Amazon and collect money from the client.
So at that point, they would care about what Amazon charges them, as well as the profit margin that they make.
Right. But they're not trying to ask, how can our client maximize resource utilization? They're asking, how can we meet our obligations to the client with us making the most money?
Right. So this could this fit in at all? I learned recently about spot instances and what they have about like the bidding process that Amazon lets you do based on the cost to them at that moment in time. Could there be a rule that somehow accounts for a constantly changing cost to the underlying infrastructure?
So there's some fun papers recently about like trying to figure out, let's say you have an application that on average uses 80 instances, but at most uses 120 and at minimum uses 40. How many spot instances do you use and how many reserved instances do you use? Integrating that sort of complexity into a model like this might be possible. Like maybe you could have pass and you could have pass spots. Haven't done any experiments. That's something to look into, but it might be kind of like a 2.0.
Yeah.
What about using machine learning on trying to estimate the cost of a query for you?
So this line is sort of a k-nearest neighbors approach to query performance prediction. Basically, we ran a bunch of the queries that we were getting in isolation, and then when we were doing the actual placement, we said, all right, what situation do we look the most like? And we'll just use that latency and see how it works out. And we're beating that. That's good. But I think most of the approaches to query prediction that are getting those sort of 15 to 25% accuracy rates are machine learning based, right? Yeah. Yeah.
So there's already a lot of research in that area.
Yeah, there's a lot.
Yes. And the state of the art is about 18 to 20%.
That's pretty good.
Yeah.
Or pretty bad, depending on where your boundary is. Yeah. So yeah, thanks for coming. We'll be presenting a similar talk at this VLDB, so if you thought anything was horrendously unclear or too quick, please let me know so I can embarrass myself